These two pictures, what do they have in common? I can draw some pixel art, or I can imagine a giant donut, and myself, sitting here and watching the donut through the screen surface. But both situations are eventually about assigning each pixel a color. This is my Python notebook for today. We start with a pixel array 16 by 8. Each number represents the color of a pixel. Now everything should be black. We export it to image format, and yes, the whole image is black. If we change these pixels to white, we will have a white square. Now we have a bigger picture size, let's say 1080p. How can we draw 3D objects? The usual way to think about it is to imagine ourselves inside a 3D scene, and we, as observers, are sitting somewhere on that axis and looking through the frame. Everything inside the viewing cone will be projected to the screen surface and form the picture we see. Just like this pyramid. Let's start with a single vertex. It could have coordinates 2, 1, minus 1. We need to find the pixel on the screen on which this vertex falls. We connect the vertex with the observer. The intersection of the screen surface and this line is the projection point we want to find. We need to find x and y components of this point in screen coordinates. We are free to set up any distance as we like, so let's decide that the screen is 1 unit wide and 16 by 9 long. How to find the projection onto the screen? Let's start with the y coordinate. We know the vertex y coordinate and all the distances in the triangle. We need to find y projection. Those two triangles are similar, and we can easily find the scale factor and y projection coordinate itself. The same for the x component. We have two similar triangles again, and all the distances and the scale factor are the same. Back to the Python notebook. We create a 1080p screen of black pixels and a very simple class just to contain x, y and z vertex coordinates. This way we can create a vertex and access its coordinates. And finally, the function that takes a vertex projects it to the screen surface and draws pixels in the pick array. First, we need the scale factor, k, the one we calculated looking at the similar triangles with eye distance, screen distance and so on. Let's print projected coordinates. For our vertex 2, 1, minus 1, the result is 0.8 and 0.4. The screen x boundary is 0.88, so the result looks reasonable. Let's find the corresponding pixels. We need to shift the origin and multiply coordinates by the screen resolution. Pixel coordinates look reasonable as well, somewhere close to the upright screen corner. Let's add another vertex, minus 1, 1, minus 1. Its projection falls more to the left. Now we understand how vertices are positioned inside a 3D space, and we know projections coordinates. Let's finally draw the pixels. A small screen boundary check, flipping y to match Python array order with a CV2 image format, and finally set the pixel color to white. Let's check the picture. It is hard to see, but our projected vertices are here. Let's make them more visible and draw small circles instead of single pixels. This function draws a circle with a center at x-proj and y-proj. Loops for I and j from minus size to size form a square. We exclude pixels that are outside of the circle and draw the rest. A circle radius would be 32 pixels. And we have two circles. I want further away vertices to look smaller. Let's decide that 32 will be a size for vertices at the distance of 1 unit, and the real size would be 32 divided by the distance. So we need to keep the distance from a vertex to the observer. Simply a Pythagorean theorem. Now instead of size 32, we pass the distance from the observer. And that vertex looks a bit smaller. Let's make further away vertices to look more dark. The same idea, divide the color by the distance. But this time I will smooth it a bit to make it not completely black. This is too dark. Let's keep more base color. This is better. Let's make it move. We will move the orange vertex further away from the screen. From -1 to -4. Back to the notebook. Lean space here means that t goes from 0 to 3 in 100 steps, so z goes from -1 to -4. Each iteration we create a vertex at its initial position and shift it further and further away. This time we have a moving picture, so we need to save each frame into a GIF file. The point moves in the wrong direction. A small mistake here, it should be -t. Now it moves correctly and becomes smaller and smaller. I hardly see it in the end. We forgot about the blue vertex. Let's rotate it around the vertical axis. We do it the same way. Each frame we create a vertex at the initial position. We rotate it around the vertical axis and draw it. How to find vertex coordinates after the rotation? For me, the easiest way to think about it is this. Let's say the vertex has coordinates x0 and y0. For instance, 3 and 0.5. What does it mean? It means that if we have basis unit vectors I and j, we go 3 times along I and 0.5 times along j. In other words, the vector v is a sum of 3 times I and 0.5 times j. The trick here is not to rotate only the vertex alone. Let's rotate it together with I and j. For the vertex, nothing changes. It ends up at the same spot. But the rest of the calculations becomes very simple. The vector equation stays the same. To get to the point, we need to go 3 times along I and 0.5 times along j. What is different? I and j now have different x and y components, which are projections of a unit basis vectors to x and y axis. So this way we can calculate both x and y coordinates after the rotation. We can put new I and j vector components into the matrix and name this operation a matrix multiplication, which is just another notation for the same thing. And in Python it takes just one line. In 3D space we have 3x3 rotation matrices. 3D matrices for rotations around different axes look similar, with a bit shuffled sine and cosine elements. Back to the code. We add a second vertex at its initial position. We add a rotation matrix with the angle theta, which becomes bigger and bigger from frame to frame. And each frame we multiply the initial vertex position by this rotation matrix. As a result, it seems like those tiny vertices are moving correctly. Let's finally create some shape, a cube. It will consist of dots on its surface. So we go through all the 3D grid dots, from -1 to 1 in all 3 directions, but we skip all the inner dots and save only surface ones. The cube is rather big. Let's move it 2 units further from the screen to fit the screen frame. Looks like a projected cube. We have a small problem. These small dark gray dots should not be visible behind the front ones. Let's sort vertices by the distance and draw them from the faraway side towards the front side. This way closer dots will overdraw and hide further dots. And finally rotating the cube, which means that for each frame we will generate the cube at its initial position, rotate each vertex and draw them. So we iterate over theta. We rotate each vertex, Move them further away by 2 units, sort by distance and draw them. This is how the generated GIF file looks like. The cube is rotating. We can't leave it without making a donut. With the phi inner loop, we generate a small circle of 24 dots. We shift these dots to the right by the distance of a big radius. And we rotate the circle around the y-axis by the angle theta. And this way, iterating over theta from 0 to 2 pi, we will cover the whole donut surface. We shift it 2 units away and draw all vertices. This is our donut side view. And the last step, rotation. Again, each frame we generate a donut within phi and theta nested loops. Now we will have the extra outer loop. Rotation theta will be responsible for rotating the whole donut. This time we will rotate the donut around all 3 axes with different speeds. Each rotation will have a separate rotation matrix. So we apply 3 rotations one by one to each vertex. Shift 2 units away and sort all vertices by the distance from the observer to draw them in the correct depth order. This donut looks much better, and I am actually really happy about the result. But creating shapes from single vertices is not the way real graphics work. They use triangles everywhere. So how to draw a single triangle? Let's say we successfully projected a triangle's vertices to the screen. We need to color the pixels inside the triangle. How to understand which pixels are inside the triangle and which are not? It doesn't seem very easy to me, but we can decompose this problem. Can we color a triangle with a flat bottom? We know the height of this triangle, and we know the slopes of both sides. The bottom itself is very easy to color, just coloring a horizontal line from x start to x end. After that we go 1 pixel up. The slope of the left side is 11 over 12, so each time we go 1 pixel up, the left boundary moves by 11 over 12 pixels. The same on the right side. Each time we go 1 pixel up, the right boundary moves by 2 over 12 pixels. For each horizontal line inside the triangle, we know where to start and where to end. This way we fill the whole bottom flat triangle. Go back to the notebook. This function will color a horizontal line of pixels. We will work in screen surface coordinates, so let's have a simple class for 2D vectors. And the main part, the function which gets 3 projected triangle vertices and colors the triangle. I will sort vertices just for convenience. I want the top vertex to be v1, the bottom left vertex to be v2, and the last one to be v3. After that we calculate the height of the triangle and both slopes, left and right. And we go line by line, from the bottom to the top, calculating horizontal line boundaries using slopes and coloring horizontal lines. Let's try to draw a bottom flat triangle to see if it works at all. Looks good. A top flat triangle in general works exactly the same, but we need to do some adjustments like inverting slopes. And this is a top flat triangle that we get. But how to draw an arbitrary triangle? Very simple. We will split it into 2, bottom flat and top flat, which we can already draw. This function takes 3 projected vertices and draws the triangle. First we do a sanity check. All the vertices should be different. After we sort vertices so that v1 is the top one and v3 is the bottom one. It could be that the triangle is already top flat or bottom flat. We just need to call the corresponding function and return. Otherwise we split it. Let's calculate the coordinates of the split point, v4. Its y-coordinate is the same as v2 y-coordinate. This is dy3 this is dy1. So we have two similar triangles. This distance is L. And this small segment is x, which we can derive from similar triangles. So v4x component is v3x minus this segment. What's left is to draw a top flat and a bottom flat triangles. Let's try to draw a triangle. This is what we have and it looks correct. I made a small inaccuracy here. If all three vertices have the same y coordinate, we will get division by 0, because the triangle height will be 0. Let's skip such triangles. Now we have everything to handle a 3D triangle. We were using the draw vertex function to project and draw a single 3D vertex. Now we need just to project it and return a projected 2D coordinates. Let's also have a class for a triangle, which just contains its three vertices. We use deep copy here to have a unique vertex instance, because I want this kind of code to work. Here we construct different triangles using the same four vertices. And finally we draw a 3D triangle. Project each vertex and call the function drawProjectedTriangle. Let's try to draw this triangle. Looks correct. Let's build a cube out of triangles. We create 8 cube vertices and cover the cube's surface with triangles. Each side will consist of 2 triangles, so we create 12 triangles. We rotate each vertex of each triangle around y with a rotation matrix exactly as we did before. And this is the result. The cube is too close to the screen surface and doesn't fit. Let's move it 2 units further. It starts to look 3D. But the cube is completely white. Let's color it. This is our plan. For each triangle we assign colors to its vertices. And we will spread these colors all over the triangle, like butter over a piece of bread. Let's focus on triangle sides. We start with the left vertex. Each time we come closer to the red or green vertex, we add more red or green color. So by the end, we reach a target color. Each time we go 1 pixel to the right, we add 15 to the green component. Each time we go 1 pixel along the other side, we add 23.5 to the red component. How to calculate the color of that pixel? We start from the left vertex. Go 5 times to the right and 2 times along the left side. So the result color is the color of the left vertex plus 5 times incrementing it along the bottom side plus 2 times incrementing it along the left side. It looks familiar. What if we say that the bottom side would be vector u and the left side would be v? And our pixel will be a vector p. Then the vector p would be 5 over 11 times u plus 2 over 7 times v. Full vector u corresponds to plus 165 in green. Full vector v corresponds to plus 165 in red. Those two formulas have the same meaning. Let's summarize this idea. For each triangle, we set up the internal UV vector bases. Each pixel p inside the triangle will be decomposed in this UV bases. As soon as we find alpha and beta, we know the color of the pixel. If we write down all the vector components, the decomposition looks like this. Those are the numbers we know, and alpha and beta are to find out. In fact, this is just a system of 2 linear equations. We can easily solve it manually, but in Python it takes just 1 line. Back to the Python notebook. Each instance of vertex 3D will now have its color. So when we create a triangle, we have to specify the color of each vertex. Let's do it. I will use colors from pastel color palettes. We will soon calculate internal UV basis vectors. I want to store them in the 3D triangle class. This function takes vertices projected coordinates. It is a very good moment to calculate u and v. Simply subtract v2 minus v1 and v3 minus v1 coordinates. We also need to save the origin, which is v1. Now instead of hard-coded 255 color, we pass a triangle 3D which contains both U and V. And we are in the function that iterates through triangle's pixels. For each pixel, we calculate alpha and beta. This function implements the solution for the system of two linear equations. So we get alpha and beta, calculate colors distribution along U and V, and calculate the resulting pixel color. FillPixel function now takes RGB arguments and sets all three colors to the image. The pixel array now has three layers, R, G and B, and this is the result. It has visibility problems. Backsides are visible and this is not correct. It happens because backsides are rendered later and override frontsides. We can fix it. We want to draw this pixel. And this pixel is a part of this triangle. We can save the distance between the triangle and the observer. If we have another triangle that is projected to the same pixel, we check the distance again. And don't draw it if the distance is bigger. For each pixel, we will store the information about the distance to the 3D point being projected and drawn. So when we want to draw a pixel, we check this information. If the currently drawn pixel is already closer to the observer, we will not overdraw it. So for each pixel, we keep its current depth and call this mechanism a depth buffer. But how can we find the corresponding 3D triangle point for that pixel? Good news. Any triangle's point in 3D space could be decomposed into U and V bases as well. When we project the triangle to the screen surface, the point is projected too. U and V vectors of the projected triangle are different, but alpha and beta stay the same. So this is our plan. We have a pixel, we decompose it to alpha and beta, we go back to the 3D triangle, apply alpha and beta to the 3D UV bases, and find the point in 3D space which was projected to our pixel. Now we can get the distance between that point and the observer and put it into the depth buffer. Back to the code. Let's calculate U3D, V3D and the origin. This function takes already calculated alpha and beta and returns the depth of the pixel point using UV decomposition in the 3D triangle. We pass it further to the FillPixel function. Now before drawing a pixel, we check if our pixel is visible or not. Now along with the pic array with pixel colors, we have another array of the same size which contains depth information. We pass it to all the functions. Let's add more rotation to make it more interesting. The extra rotation around x-axis. And this is the result. This looks good, and I am happy about the result again. Using UV decomposition, we can add a very simple light source. This is a light source and this is a triangle inside a 3D space. We want to understand how bright is this area. We construct a normal unit vector to the surface at this point. Normal vectors are the same at every triangle's point and can be calculated using this cross product formula. We draw a unit vector towards the light source. We are interested in theta. If theta is close to 0 degrees, the brightness is very high. If theta is close to 90 degrees, the brightness is very low. We can calculate theta. A dot product of n and l is easy to calculate using coordinates. But on the other side, it is equal to the cosine of the angle between unit vectors. To find the brightness of the pixel, we need to find the cosine of theta. Each point of the triangle has a different theta. We need to solve about the same problem. Having a projected pixel, we need to find its 3D counterpart, reconstruct the vector to the light source and calculate the dot product. But we can make a shortcut here. These are three normal vectors to the triangle surface from its vertices. We can pre-calculate dot products for them and spread over the triangle using UV decomposition. UV decomposition helped us again. Let's write this code. We calculate a normal vector as a cross product of u and v. And we calculate 3 dot products of the light vectors and normal vectors for vertices. So we have a cosine theta for each vertex. After that, we need to call this function. And the final touch, calculate the dot product for a specific pixel and adjust the brightness. What we've done is far away from being perfect. Maybe it is not even correct sometimes. But making something simple is accomplished.